right, guys, before we get started, are there any questions over the homework? Okay. So from 6.5, we'll look at problem number 29. 5 natural log of 2 plus 7 natural log of x plus 4 natural log of y. So when we look at this here, the first thing, when we condense, we had our first step was powers. So we put all the powers back up. Exponent. So the number in front, power rule said if there's an exponent inside the log, we can move it to the front. We can also go the other direction. If there's a number in front of the log, we can move it back to an exponent. So 5 times the natural log of 2 is the same as natural log of 2 to the 5th. Plus 7 times the natural log of x is the same as the natural log of x to the 7th. And 4 times the natural log of y is the same as the natural log of y to the 4th. Now, if there had been a minus in front of any of these numbers or minus the natural log, we take the negative with it just to make it a little bit easier to work with. Our product property with logs we're going to use next, because if we have 2 or more logs being added together, the same log, we can rewrite it as a single log with what's inside each of the logs being multiplied together. Questions on this so far? Now we just need to simplify where possible. The only thing we can simplify here is 2 to the 5th, which is 32. And the other one we'll look at is 30. So again, we're wanting to condense this. You're welcome. Now again, the first thing we're going to do is powers. Now there's only one power that we can do, and that's the 2 in the middle. So we still have log base 3 of 4. But now we have plus log base 3 of 1/2 to the 2nd plus log base 3 of x. At this point here, we have 2 or more logs being added together. So we can rewrite it as a single log with what's inside being multiplied together. Now the 4 times 1/2 squared, we can simplify this. Now 1/2 squared is 1/4. And if we multiply the 1/4 and 4, we get 1. Which just tells us it's log base 3 of x. Yeah. Any other questions on the homework? What we're looking at today is solving. Today is going to be our first day of solving logarithmic and exponential equations. Now, the book calls this property of equality for exponential equations. Another way, or another term for this property, is the 1-to-1 property, 1-to-1. And what it says is if b is a positive real number other than 1, then b to the x is equal to b to the y if and only if x is equal to y. What that means for us is if we look at this equation and we have one base on either side and they are the same, the only way that these two can be equal is if the exponents are equal. So the only way that 5 to the 3 minus 2x is equal to 5 to the negative x is if and only if 3 minus 2x is equal to negative x. If the bases are the same, we set the exponents equal to each other. Okay. Questions on this so far? You ready for the next step? Solve for x. So since we don't have an exponent, we don't have an x squared, x cubed, x to a power greater than 1, get x by itself. So what can we do? We can add 2x. Negative x plus 2x is x. X is 3. And that's it. Now, if we want to, we can check and make sure this works. And all that is I take our value of x that we got, 3, and plug it back in. And we just make sure that both sides are the same. Now, on the left-hand side, we have 3 minus 2 times 3. Negative 2 times 3 is negative 6. 3 minus 6 is negative 3. On the right-hand side, negative 3 is just negative 3. Well, 5 to the negative third power is indeed equal to 5 to the negative third power. We don't have to turn it into fractions. We don't have to simplify it farther than that. It is the same. They are equal. Questions on the first problem? Our next one, 6 to the negative 2a is equal to 6 to the 2 minus 3a. Are the bases the same? Yeah, they're both 6. Do we have one on either side? Yeah, one base either side. So the only way this works is if negative 2a is equal to 2 minus 3a. There we go. All right. What can we do first to solve for a? Add 3a. Questions on these here? We ready for the next one? Three to the 2a equals 3 to the negative a. Bases are the same. We have one on either side. So that means that 2a is equal to negative a. What can we do first? We can add a to both sides. 2a plus a is 3a. Negative a plus a is 0. We have 3a equals 0. There's really two different ways we can go about solving this. One, zero product property. Zero product property stated what? If I multiply two things together and get 0, one of them has to be. So if we look at this here, I have 3 times a equals 0. I can't change 3. It's just telling me what? A has to be 0. The other method, divide both sides by 3. 3a divided by 3 is a. 0 divided by 3 is, we get there either way. Do we feel comfortable with these here? Do we need to see another example of one of these? I mean, the only thing that's going to change is that we make the equations and the exponent quadratics or more in solving. But the property is still the same. If the bases are the same, we set the exponents equal to each other. You're welcome. So looking at this next one here, Are the bases the same? Yes. Is there one on either side? No. Because if we look at the left-hand side, we have 6 to the 3m times 6 to the negative m. Well, according to our properties of powers, a to the b times a to the c, if we multiply like bases, we add the exponents. This is our product property with exponentials. So that means for us, that 6 to the 3m times 6 to the negative m is the same as 6 to the 3m plus negative m. We can add those exponents. Because for us to use this one-to-one property, this property of equality, we need one base. We need that 6, only one of them on either side. Now 3m plus negative m is just 2m. Because really our goal with this one-to-one, that makes it nice, is that we have the same base on either side, and there's only one of them. Now since we have 6 to the 2m equals 6 to the negative 2m, bases are the same, so that means the exponents have to be the same. Add 2m, telling us 4m equals 0, or we can say what? M is 0. Questions on any of this so far? We feel good with number 9. Yes? Let's look at number 13. Well, 13, left-hand side, we do have 4 to the negative 2x times 4 to the x. So as we just saw, since we multiply like bases, we can add the exponents, yes? All right, so now both sides are to the base of 4, yes? No. The other side is what? 64, yes? Now, if we could rewrite 64, if there's a way, an equivalent version of 64 that is 4 to a power, that would make this work out nice, yes? Is there a power of 4 to a power that gives us 64? So since 4 to the third is 64, we can replace 64 with 4 to the third, so the bases are the same. Now, this isn't the only way we could have done it. We could have written both of them to the base of 2. Plus 2 squared is 4. 64 is 2, I believe, to the 6th. Yes. So we could have done it with the base of 2. It's just the numbers would have been a little bigger. We would have got the same answer, but the numbers would have been a little bit bigger. Questions on how we got this here? Now the bases are the same, so it means we can set the exponents equal to each other. And yes, we could have combined our negative 2x plus x before we did that. So negative x equals 3, yes? Well, we don't want to know what negative x is. We want to know what positive x is. So we can either multiply or divide by negative 1, and we get x equals negative 3, yes? So, yes, because this 3 here are how we got it here.
No, how you got it.
So, yes, that is a good question. It's kind of how we got this 3 here, yes? So, at this point here, we're able to rewrite the 2 so they both have a base of 4, yes? So that's the same. We're saying 4 to a power. 4 to what power is going to make these equal? Well, the only way this works is if these two exponents are the same. So if those exponents are the same, they're going to be equal. No, you're good. No. Yep, so the 4 essentially for this here is disappearing. Now, let's dig into this a little bit deeper. Now, we've had this one already. Log base b of b to the x. We did this in 162. So y'all remember doing this here, yes? Log base b of b to the x is what? Just x. It's that exponent. Now, the reason for this is, well, according to 6.5, if there's an exponent inside the log, we can move it to the front. So this is really the same as x times log base b of b. Well, log base b of b is 1, so it's telling me that log base b of b to the x is just that exponent x. Yes? So we're going to get into this, especially with these logarithms. But what we can do, and what we're really doing to this here, is I'm applying both sides to the log base 4. Now, I picked 4 for a reason as the base. And we'll simplify that to negative x. Now, I applied log base 4 to both sides because here we have log base 4 of 4 to the negative x. And as we just stated, this here, according to what we just looked at, would be what? Negative x, yes? The other side, log base 4 of 4 to the third. Again, it's just going to become that exponent, which is, this is why this works. Because if those bases are the same, like the previous one, I can apply log base 6 to both sides. Well, I'm going to put it down one. And here, the log base 6 of 6 to the 2m is just going to become 2m. Log base 6 to the negative 2m is going to become negative 2m because that log base 6 of 6 is 1. That's why this one-to-one property works. So this kind of makes some sense. Now we'll start digging into this, especially when the bases are not the same. When the bases are not the same, we have to start going with this kind of method to get them to be the same. But that is not today. So let's look at this next one here. We have 100 to the x is equal to 1/10 to the x minus 3. So if we can get the bases to be the same, the exponents have to be the same as well. So let's start with 1/10. Because if we can rewrite 1/10 as 10 to a power, well, it'd make things a little bit nicer. Now for this here, all we did was take the 10 from the bottom of the fraction and move it to the top, which is possible, but whenever we do this, we have to change the exponent from positive to negative, or negative to positive. Well, 10's exponent's 1, so when we bring it to the top, it becomes 10 to the negative 1. Now for this here, 10 to the negative 1 is indeed 1/10. Incidentally, 1/10 to the negative 1 is 10. So that does give us 10 to the negative 1. Now the question is, 10 to what power gives us 100? 2. 10 squared is 100. So now are the bases the same? Yeah. So these here, even though the bases did not start out the same, if we can get them to be the same, then the exponents are going to have to be the same as well. Now before we set the exponents equal to each other, it might be nice to rewrite them or simplify them a little bit. Powers of powers, multiply. Here we're going to distribute the negative 1. Negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. So what we have is 2x is equal to negative x plus 3. What can we do next? Add x. And lastly, divide by 3. And that's it. There are other ways to solve these here, but especially it works very nicely if we can get the bases to be the same. Because once the bases are the same, we set the exponents equal to each other and solve. Questions on problem A before we look at problem A? Questions on problem A before we look at problem A? Okay, we ready to look at problem A? Yes. 81 to the x is equal to 1/9 to the x plus 3. So it'd be nice if we could rewrite these so that the bases are the same. Now the 1/9, we can move the 9 from the bottom of the fraction to the top. 81, we could rewrite it as what? 9 squared. Incidentally, we could have used 3, because 3 to the 4th would have been 81. 3 to the negative 2 would have been 1/9. Powers of powers. Multiplying. So 9 squared to the x would be 9 to the 2x. 9 to the negative 1 to the x plus 3. We can distribute the negative 1, giving us negative x minus 3. Since the bases are the same, the exponents have to be the same as well. We're going to add x to both sides. 3x equals negative 3. Divide by 3. X equals negative 1. Questions on these here? Not always, but we feel good with these here. We'll look at one more. Let's look at the 7 one. It's not on your paper. I added it this morning. Yes. Now, if we're going to solve this by the one-to-one property, we need to be able to rewrite 343 as 7 to a power. 7 to the third, yes. Because otherwise we'd have to find or use another method to get there. Now, before we can just set the exponents equal to each other, it's going to be nice if we simplify this here. Powers of powers multiply, so our 3 times x would give us 3x plus 12. Since the bases are the same, we can set the exponents equal to each other as well. Now we just need to solve for the value of x. Minus 2x from both sides first. Will tell us that negative 3 is equal to x plus 12. Then we can minus 12 from both sides. Knowing this x is equal to negative 15. Yep. Questions on these here? You ready for the next step? Property of equality with logarithms. Again, this is just the one-to-one property again. If the logs are the same and are equal to each other, this is only true if and only if what's inside is equal as well. So we look at this first one here. Well, we have one log on either side of the equation, and they're both the natural log. So they are the same. So that means what's inside the logarithms has to be the same as well. So that means for us that 4x minus 7 has to equal x plus 5. We can subtract x from both sides. Telling us that 3x minus 7 is equal to 5. Add 7 to both sides. 3x is equal to 12. Since the logarithms are the same, what's inside them has to be the same as well. Now we could check this and make sure that this works. And we'd say that the natural log of 4 times 4 minus 7 is equal to the natural log of 4 plus 5. So on the left-hand side, our 4 times 4 would be 16. Natural log of 16 minus 7 would be the natural log of 9. On the right-hand side, 4 plus 5 is 9. The natural log of 9 is indeed equal to the natural log of 9, so this works. Now we can have extraneous solutions with the logarithms because the number inside this final number cannot be 0 or negative. We cannot take the natural log of log of 0 or a negative number. So if a solution that we have, when plugged back in, gives us a logarithm of 0 or a negative number, it does not work. It's fine with exponents. We cannot have 0 or a negative number inside the log. So here 4 gave us 9 and 9, that's fine. Even if it said the natural log of negative 9 is equal to the natural log of negative 9, it would not work because we cannot take the natural log of negative 9. Questions on this here? Let's look at the next one. Natural log of 7x minus 4 equals the natural log of 2x plus 11. Since the logs are the same, and there's only one log on either side, you can set them equal to each other. And now we just need to solve for the value of, all right, so we can subtract 2x from both sides. 7x minus 2x is 5x minus 4 is equal to 11. Then we can add 4. 5x is equal to 15. Divide by 5. Questions on this here? Do we feel comfortable with these here? 11 or 12? Which one do y'all want to look at?
Yeah, that's what you choose.
We can do both. Log base 12 of v squared plus 35 is equal to log base 12 of negative 12v minus 1. Are the logs the same? Yeah. So since the logs are the same, it means that v squared, or well, this is supposed, I think, has x on y'all's. Yeah.
It's not the x in the
Since the logs are the same, we can set what's inside each of them equal to each other. So I'll switch it over to x. X squared plus 35 equals negative 12x. Now this is a little bit different than the ones we've had before because this time we have an x squared. That means we need to get this equation equal to 0. So the first thing we could do is add 12x to both sides. If we add 12x to both sides, we get x squared plus 12x plus 35 is equal to negative 1. At this point, we can add 1 to both sides, telling us x squared plus 12x plus 36 is equal to 0. Now at this point here, we could factor, graph, or do the quadratic formula. I would stick with either factoring or graphing. So we can factor this. So 2 sets of parentheses with 3 spaces. Since the third term is positive, the signs are the same and match the sign of the middle term. Factors of the first and third term are the only factors of x squared, x and x. Factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. Well, 6 and 6 are the one we want. Now, since we have 2 or more expressions multiplied together to equal 0, one of them has to be 0. So we can set both of them equal to 0. Solve for the value of x. Right. Negative 6. So the other one we also get negative 6. So we get 2 solutions. They're just the same solution. So negative 6 is our solution here. Now, even though it is negative, let's see what happens when we plug it back in. So log base 12 of negative 6 squared plus 35 is equal to log base 12 of negative 12 times negative 6 minus 1. So we'll look at the left side first. Log base 12. Negative 6 squared, negative 6 times negative 6 would be 36. And our 36 plus 35 would give us log base 12 of 71. Let's look at the right side. Negative 12 times negative 6 is going to be positive 72. And 72 minus 1, 71. They are indeed equal to each other, and the numbers we end up inside the logs are both positive. So even though the solution was negative, what we ended up inside the logs is positive. So it works. If it says check, yes. If not, you don't have to. Because the ones we get extraneous solutions are going to be these logs. But questions on this here? That's it.